Welcome to another video. Today we're going to be going through the first part of forces. It's a pretty humongous topic, so we'll probably go in different steps and cover it in multiple different videos. So here is an overview, so have a read through that and we'll begin. So what are forces? A force is a push or a pull that causes a change in speed, the direction, or the shape of an object. A spring being extended out due to a hanging ball of mass, a car moving forward, or this lady swinging this bucket around and around are all possible due to the effects of force. So basically, we're going to carry out this simple experiment that demonstrates the effect of gravitational force on a spring. So basically, we hang the spring on a platform along with a ruler on the side in order to measure the various different lengths of the spring as we place various different masses at the very end of the spring. So first, what we want to do is measure the original position of the spring, which we will name L0 for length 0. So if you take a look at this diagram on the right here, you'll see that you've got the spring and then you've got a pointer that you can use to figure out the original position of the spring. At this point, we don't have any weight, so just ignore this diagram down at the bottom here. Just ignore that we've got anything on the spring, and we just want to measure what the unloaded original position of the spring is, that is without any mass in place. Okay, now what we want to start doing is add a bit of mass to the end of the spring. And so when we add the mass, basically what that will do is create a downwards force on the spring, and that will lead the spring to extend. Remember, gravity is a force that acts on mass, and the force is called weight. And remember, weight equals mass times gravity. So for example, if you had a 1 kg mass, then the total weight on that would be 1 times 10, because 10 is the gravity that you get on Earth, creating an overall force of weight of 10 newtons. And so basically what we're doing is we're adding a bit of mass down at the bottom here, which causes a downwards force, which is weight, and that's causing the spring to lengthen or extend. So once we add the 100-gram mass, we then measure the new position of the spring, because again, the length would have changed because of that extension. And so we're going to call that L1, length 1. And so what we're really interested in knowing is what the actual extension is. What is the difference between the new length, L1, and the original length, L0? And we calculate the extension that 100-gram mass has caused. Then what we want to do is continue on and add an extra 100 grams. And so now the total will be 200 grams, and now we want to measure the new length. And again, by adding an extra 100 grams, you'll find that the spring will extend again. So the length will now be even more than what it was after we added the first 100 grams. So now we've got this second new length. We're going to name it L2. And now we want to calculate the extension caused by the 200 grams worth of weight. And so that would be pretty much the difference between L2 and L0. L0 being the original position with no masses on. And so we keep going and going and going as we add more and more and more mass, and we just calculate what the extension is at each time we add the extra mass. So if we can show this stuff, initially we've got this sort of spring looking thing, right? And this spring is going to have some sort of original length. So we're going to say, I'll do it in a different color. We're going to say that this original length is, say, 1 centimeter, for example. And if you add the 100-gram mass, okay, so it's like 100 grams, then what you will find is that there's some gravity and the weight pushes the spring downwards and it causes the spring to extend. And now the spring's new position, which is, we called it L1, right? L1 might be something like 1.5 centimeters now, okay? So L0 was 1 centimeter, now L1 is 1.5 centimeters. So what is the extension here? Well, the difference between 1.5 and 1 gives you an extension of 0.5 centimeters. And you can imagine adding an extra mass, right? This time you add an extra 100 grams on top of that. So now you've actually got a total of 200 grams, right? And now you want to calculate the new length, and we're going to call that L2. And you might find that L2 might be something like 2 centimeters. So what is the extension that is caused by the 200 grams? Well, again, what's the difference between L2 and the original L0? Well, 2 minus 1 is 1 centimeters. That's the difference. So the extension here is 1 centimeter. And you can go on and on and on until you've added, say, 600 grams or 700 grams or whatever you want to that spring. And what we want to know is at each step along the way, what is the extension that is caused by that particular mass that we've added on. So I hope that makes sense there. So basically, take a look at the experiment that we just did and we were to sort of plot that on a table here, what we can get is the mass that we've added and the force, right? Because you can derive the force by multiplying the mass by gravity. So for example, 100 grams is going to be 100 divided by 1000 first. Because we want to put that into kilograms, right? So it's 0.1 kilograms, and you times that by 10, which is gravity, and you get a total force or weight of 1. Same thing for all the other numbers. For example, 200 grams of mass is going to be 200. Convert that into kilograms, which is 0.2, and you times that by 10, you're going to get 2 newtons. And so that's the second column there of force. And now what you would have recorded is the length of the spring. Okay, the length of the spring after you've added each of these different masses on. And from that length, you can calculate what the extension is, which is pretty much the difference between all of those different lengths. The difference between that and the original length of the spring. Now in this case, I've given you some numbers to work with, and we're gonna say that when we had no mass on, the original length of the spring was 1 centimeter. So that's our baseline. And after you've added 100 grams, well, the length increased to 2. And because of that, we calculate the extension being 1 centimeters because the difference between 2 and 1 is 1. So we're looking at this area here. Now, 200 grams, when we added that onto the spring, we found that the length was 3 centimeters. And so the extension now becomes 2 because the difference between 3 and 1 is 2. And for example, when we get to say, 400, well, the length was 5, and again, the extension is just the difference between that and the original, which is 1, so the extension was 4 centimeters, and we can also convert that all into meters as well, which is what I have done on the most right table there. So basically, here are the results. But if you pay close attention, right, clearly, the larger the mass, results in a larger force that's applied, or the greater the weight, and hence the greater the extension on the spring. But I want you to pay close attention to the pattern between force and spring extension. Do you see how for the first 400 grams that we've added, each time we've added the extra 100 grams, the extension goes up by exactly 1 centimeter. So for example, when we went from nothing to 100 grams, we extended the spring by 1 centimeter. When we added an extra 100 grams on top of that to make it a total of 200 grams, the extension was 2 centimeters. And so at each time we've added 100 grams, the extension was an increase of 1 centimeter. Up until this point here, when we add an extra 100 grams from 400 to make it 500, now the extension isn't 1 centimeter increase, it increased by actually 1.5 centimeters. And you can see that from 500 to 600, again, instead of it going up by 1 centimeter, it actually went up by 1.5 centimeters. And eventually from 600 to 700 grams, it jumped by a huge margin of 5 centimeter increase. Okay, so what we can infer from this data is that for the first 400 grams of incrementally adding 100 grams on the spring, there is proportionality between the mass and, or in other words, the force that we apply and the extension of the spring. I hope that makes sense. So basically, if for every 100 grams that we add, there's a constant increase of 1 centimeter extension on the spring. So that's proportionality. But things don't seem so proportional after that 400 grams, right? Because again, you would expect from the previous four plots of data that from 400 to 500, you would, when you add 500 grams of mass, you'd get 5 centimeters of extension, but here you actually find you get 5.5. Same with 600, you can see it's not proportional because normally, from the first few points, you'd expect 600 grams to give you 6 centimeters of extension, but you actually get 7, which is more than what we'd expect. And 700 is the same thing. You would expect 7 centimeters of extension, but it doesn't follow that pattern any longer, and there's a huge increase to 12 centimeters of extension. And so it's pretty easy to visualize all this when we sort of plot this on a graph. And so what I'm going to do is I'm going to pause this video and I'm going to draw the graph on my iPad and sort of show you guys how I would plot this data. And I'm going to use centimeters in the x-axis for the extension for this. So I hope that was useful, but here is the end result of the extension graph, or the force extension graph that I drew for you using the data, which is all hypothetical, but using that data that I showed you on the table. So pretty much here you can see that there is initially the straight line. Right, there's 3 parts to the graph, but initially you see the straight line represented by the green. And this is the area or the region where the force and the extension are proportional. That's the first few points of data that we had on this table, between 0, 100, 200, 300, 400, where at each step along the way we had a consistent increase of extension of 1 centimeter. So that's what is represented by this green plot. And it's a straight line, right? And because it's a straight line, we know that the y-axis and the x-axis are proportional, right? So eventually, though, you start to find that the gradient becomes less steep and the graph starts to flatten out a little bit. As we add more and more force, in other words, later on, from around 4 newtons onwards, the spring extends much more than what it did before. For the same 100 grams that we've added, the extension is more than what it was before. That's why the graph is flattening, and that becomes more pronounced as we add more and more force. Um, so now a spring can usually handle a lot of stress, but when you get to the stage where the force is not proportional to the extension anymore, that's when you're potentially going to start to damage the spring. And that's what we're actually seeing over here. So as I said, the green region is the flat line that demonstrates the proportionality between the force and extension. This is pretty much the safe zone, and that's how most springs act for a good part of the 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 pattern as you add more force to it. But this blue region here is when that proportionality starts to fail. As you can see that the graph is starting to flatten out a little bit. And so basically here at this blue point here, the spring is indeed extending a little bit more compared to the force that's being applied. And when this proportionality, when the graph starts to fall off a little bit, that's when we know that the limit of proportionality has been reached. And after that point, things are not so proportional any longer. But the interesting thing about this point is as long as you just take off the load and you take off the weights that you've added, then the spring bounces back to its original shape. As I said, springs usually can take a lot of stress, and so it takes a lot to damage it. So once you take off that load, then it goes back to what it was before, all pretty normal. But here you start to find that things are getting a bit too much. You're adding so much force that the spring is extending significantly more, right? And that's when we know that the elastic limit has been met. Once you pass the elastic limit, you've gone to the point of no return. Even if you unload the weights now, the damage has already been done, and the spring will not return to its original shape any longer. You've pretty much damaged it, and nothing else can be done. So these three parts of the graph are really important. And so we're going to be talking about the Hooke's law in a second. But before we go into that, it's really important to understand that when you calculate the gradient, especially before the limit of proportionality, what you're really doing is just calculating the slope. Now, when you calculate the slope within this green region here, what are you doing? Well, you're measuring the change in the y-axis, and you're dividing that by the change in the x-axis. So what are the units on the y-axis? It's force, and the units down at the bottom axis is the extension, which is in centimeters. So it's newtons divided by centimeters, and this will become relevant in a second. So here is a typical representation of what an extension load graph or a force extension graph might look like. You've got the force on the y-axis and the extension on the x-axis. So the Hooke's law suggests that the extension is directly proportional to the force applied until the limit of proportionality is reached. So every spring pretty much behaves this way. For a good part of its behavior, you have the force being completely proportional to the extension of the spring, up until a certain point when that proportionality starts to fail, right? So as long as it's before the limit of proportionality, which is this straight part of the graph here, or in other words, the green zone that I talked about before, then that's when you can apply something called the Hooke's law, which has this formula where F equals the force applied. So F equals kx, k being the force constant for an object, and x being the extension, right? So basically, the force constant is to do with the material of the spring. It's pretty much the object's or the spring's unique property that determines how much it will actually expand or extend per force unit. After all, let's imagine you apply 3 newtons of force onto the spring from our experiment, and that led to an extension of how much? It was 3 centimeters, right? If you go back to our graph here, when we added 3 newtons of force, it extended by 3 centimeters. But does that mean that every single spring out there in the world also extends by 3 centimeters when we add 3 newtons to it? That's certainly not the case, because some springs might extend by 10 centimeters and another spring might only extend by 1 centimeter. So every spring is different and it behaves differently, and the reason for that is because they have different force constants, which is determined by the material of that spring. And so we can actually calculate the force constant of a spring by rearranging the formula of this particular equation. And so basically, if you have F equals kx and you want to find k, which is the force constant, then you can put the x on the other side to make k, which is force constant, equivalent to, well, k equals F divided by x. Because if you want to divide, you divide the right hand side by x and you put it over to the other side, you do the same, so it becomes F divided by x. Okay, so pretty much force divided by extension becomes the the formula for the force constant. And so given that you've got the data, which is pretty much what we did over here, where we added various forces and we looked at the extension, you can actually calculate the force constant for that particular spring. So for example, if you take a look at here, we applied, say, remember, this is all you need the Hooke's law and its equation only works before the limit of proportionality, and we know that the proportionality fails after the 400, so we're not going to look at 500, 600, 700. We're only going to look at the ones before that. So when we added 4 newtons, that caused an extension of 4 centimeters, right? And remember, after rearranging the formula, what was the formula for the constant? Well, the constant is equivalent to force divided by extension. So in this case, we have the force being 4 newtons and you divide it by 4 centimeters. So you have the force, or you've got the force constant of the spring being 1 newtons per centimeter. And that is a constant. So when you repeat that formula and you plug in all the other numbers, you'll get the same result. For example, when we added 2 newtons to the spring, you got an extension of 2 centimeters. So again, if you wanted to calculate the constant, 2 divided by 2 is going to give you 1. Again, 1 newtons per centimeter. So it is often good practice to convert everything to meters first, by the way. So quite often you'll find that the constant will be in newtons per meter, okay, which is usually the correct metric. But here we use centimeters, but you could have done the same and with meters and gotten the same result. But remember how I said that you can use this graph to calculate the constant as well, using the gradient. Remember, when you calculate, well, when you plot everything on the graph and you calculate the gradient, what you're doing is you're dividing the y-axis by the x-axis. And the y-axis here is the force, and the x-axis is the extension, which is in centimeters, which is basically the formula to calculate the constant. So when you calculate the gradient of the straight line part of a force extension graph, what you're actually calculating is the constant, or the force constant for that particular spring. Okay? And pretty much everything else is, we've covered that before. Here, between the limit of proportionality and the elastic limit, this region here is sort of that blue zone we talked about, where you're adding quite a bit of stress and the spring's not liking it, but as long as you take the weight away, then the spring returns back to normal, completely fine. But once you pass that elastic limit, then you've done it. You've pretty much broken the spring, and the spring will permanently be malformed and will not go back to its original position. So I know that that was a lot to take in, but I hope that was helpful, guys. Any question, feel free to comment below, and I will see you in the next video.